How do we find the area of a polar curve? Well, it goes back to finding the area of a sector of a circle. If we have a circle of radius r and select a sector of an angle, delta theta, where this delta theta is the change in angle from beta to alpha, then the area of the sector is given as the area of the whole circle multiplied by the fraction of that circle. Just like if that sector right here represented an eighth of the circle, you would take the area of the circle and divide by 8. Well, how do you know it's an eighth or a part? This is the part of the angle divided by the whole angle of the circle, which would be 2 pi. Now, let's reduce this formula. You can see that the pi's would reduce. You'd have a 2 on the bottom, which we would call that 1/2 r squared delta theta. So that's the area of the sector of that circle. What can we do with that? Well, now suppose we have a curve in polar coordinates. As we did with rectangular coordinates, we take small increments of theta, which we of course will denote as delta theta. So if I have some curve here, remember this is r, which is a function of theta, and I want to find the area bounded between alpha and beta, what I can do is take very, very small sectors and divide it up. So like this sector would be a little bit bigger than the area I wanted because that area is above or bigger than the actual function. Then I would take this area, and you can see that would be a little bit smaller, and so forth. And so we would have an infinite amount of these sectors. So if we let delta theta be infinitesimally small, then of course that wedge shape has an area of 1/2 r squared d theta. So what's happening in the calculus? Well, if we partition it off into many, many, many sub-intervals, right, just keep splitting and splitting, making it smaller and smaller, then we can approximate the area of this whole region by adding all those up. Now remember, that's the same as r. r is a function of theta. And of course, if we take the limit as n approaches infinity of that area, we get the definite integral. And so the area of a polar region can be defined as 1/2 r squared, which of course r is a function of theta, delta theta, between two given angles. So just like we had a function in rectangular mode, and we had many different rectangles, and some were above, some were below, and we took those Riemann sums and we added it all up together using the area of a rectangle. We do the same thing by adding up all these sectors based on a circle. So again, we could have this sector, which would be a little bit too small, and maybe this sector that would be too big. But again, as delta theta approaches 0, as we have infinite amount of these, then our approximation becomes the definite integral given by this formula. So how can we apply that formula? Finding the area inside a curve. So we have the area is 1/2 bounded between our angles of r squared d theta. We want to find the area inside this cardioid. So one thing that you have to investigate is what are your limits? What would give you that whole cardioid? Well, from 0 all the way around to 2 pi would give us that cardioid. And that would be okay. But sometimes it's a little bit easier if you use symmetry. Because of this 1/2, just so I can kind of get rid of it, I'm going to go from 0 to just pi, all right? And so those would be these sectors added up. And then I would multiply by 2 because I have a top half and a bottom half. So that's the approach I'm going to take. So I have my area is 2 times 1/2 between 0 and pi of r squared d theta. Now again, you could have gone from 0 to 2 pi and done the half. We would have gotten there. Okay, so those of course reduce out. You want to FOIL this out. And here's the hard part. You're going to be introducing usually cosine squares and sine squares, which we don't have a straight integral. You have to use the identity that cosine squared theta is 1 plus cosine 2 theta divided by 2. So that's the substitution you need to make. So we would have the area is 1 plus 2 cosine theta plus 1 plus cosine 2 theta all divided by 2. Okay, so how do I integrate that? The integral of 1 is of course theta. The integral of cosine theta is sine theta, so I'd have plus 2 sine theta. Right here, this is the same as 1/2, so I'd have 1/2 theta. This is the same as cosine 2 theta divided by 2. So you need to be careful integrating that, right? So you've got this 2 that comes out here as 1/2, and how do you integrate cosine 2 theta? It's going to be this 1/2 here, then you're going to have the sine of 2 theta, but you need to multiply by 1/2 again because of that 2. So you're going to end up with 1/4 sine of 2 theta. And we want to evaluate that between 0 and pi. So we're going to have the area equals to pi plus 2 times the sine of pi plus 1/2 pi plus 1/4 the sine of 2 pi minus, when I put in 0 here, that gives you 0, that gives you 0. The sine of 0 is 0. The sine of 2 times 0 is still 0, so that's going to be 0. Then the sine of pi is 0. The sine of 2 pi is 0. So all we have is 1 pi plus 1/2 pi, which is 3/2 pi. And that would be your area. How could you go about finding the area of one petal of the rose curve given here? Well, first of all, you need to make sure that if you are going to go from 0 to 2 pi, that traces out the curve only one time. Okay, you could verify that on a graphing calculator or some other calculator tool. Another option, now if you go from 0 to 2 pi, that's going to give you the whole curve. I only want one petal, so how could I figure out just one of those? Well, of course you could go from 0 to 2 pi and divide by 4. That's one option. Another option is to find out what would be the value of theta to give you just one petal, meaning when does r equal to 0? And I think that's what I want to do. So I'm going to say 0 is 3 times the sine of 2 pi. Dividing by 3, you still get 0. So take the inverse sine of each side. So when does 2 theta, okay, arc sine of 0, 2 theta, means I need to go around the circle twice. So when does the sine equal to 0? 0 pi, 2 pi, 3 pi. That's for 2 theta. Now divide by 2. And that is when this graph goes through the pole. Right, so I know from 0, when theta is 0, going all the way around to pi over 2. So from there to there, that would give me 1 petal. That's another option. Go from 0 to pi over 2 for 1 petal. The other option is to cut it in half and go from 0 to pi over 4, but multiply that times 2. Your choice. I think I'll just do this 1 petal. Right, so my area is going to be 1/2 between 0 and pi over 2 r squared d theta. So 3 squared is 9. I'm going to take that on the outside of the integral. Then I have sine squared of 2 theta. So here's that sine squared, just like I had cosine squared. Well, I have to now know that the sine of theta is equivalent to 1 minus the cosine of 2 theta divided by 2. Look at this angle. That's theta, that's 2 theta. So if that's 2 theta in my problem, then I need a 4 theta. Being very careful. So my area is 9/2 between 0 and pi over 2. And in place of this, I'm going to have 1 minus the cosine of 4 theta divided by 2. So I have 9/2. Then I'm just going to pull that on the outside of that. So I want to integrate 1/2. So that's 1/2 theta. Minus, then I have to integrate this. So just like on the previous problem, I have to take care of that 1/4. The integral of cosine is sine. And so I have the 1/2 because of this 2 times a 1/4 because of that 4. And then I have the sine of 4 theta. And I want to evaluate that between 0 and pi over 2. So lots of fractions. So I have 9/2 from here. Then I have 1/2 times pi over 2 minus 1/8 times the sine of 4 times pi over 2 minus, then I have 0 minus 1/8 times the sine of 0. So let's see, what do we have here? Let's do the easy part. The sine of 0 is 0, so that's all 0. That would be 2 pi. The sine of 2 pi is 0, so that's 0. So all I've got left is right there. That's my answer. 2 times 2 times 2, that's an 8 on the bottom, and I have a 9 pi in the numerator. Again, one of the difficulties with these problems is because you're going to be introducing sine squares and cosine squares, and you've got to know those identities. And the other problem is to investigate what will be your limits, and you have some options. So be careful.